Willis, and I'm going to be presenting to you about the thermocouple time constant experiment. I'm in group 4 of the section 5 for ME 4611. So system overview, we conducted this experiment last Monday. We have 4 primary components. We have a data acquisition system, a type K thermocouple, a hot plate, and a beaker filled with water. What's going to happen is we're going to fill a 500 milliliter beaker full of water. We're going to place it on the hot plate, heat that up to we get a rolling boil. Once we've reached that point, we're going to stick the tip of the thermocouple into the beaker full of water, measure the temperature, and that output from the thermocouple is going to be recorded in our data acquisition system in an Excel file. So a little background on how all this works is thermocouples measure temperature differences between a hot and cold source. They have 2 dissimilar metals which are welded at the tips, and in that junction we get a voltage difference. So by setting a temperature difference at both ends of the 2 metals, we can measure the voltage difference generated in the thermocouple, and that voltage can be converted into measurable temperature difference, which we recorded in our Excel sheet. Shown on the screen is a diagram of how you would measure the temperature difference between a cold junction and a hot junction, and how you would get output voltage from that. So our objective is to find the transient response for a 1/8 inch diameter type K thermocouple. To do this, what we're going to do is we're going to plot the data versus time, the temperature versus time. We're going to normalize the results, which should give us a maximum value of 1 in between 1 and 0. And then we're going to construct a log plot of this data. Once we have this data, we're going to estimate it using a linear trend line. If we find the slope of the linear trend line, we can take the inverse of it, and we should get our time constant for the thermocouple. So shown on the screen is some arbitrary response of a sensor, and the time constant is the amount of time it takes for the signal, which you're recording, to reach 63.2% of its final value. It is said that after 5 time constants, that the signal is within 99.2% of the steady state value. There's also other variables such as percent overshoot and those type of things that characterize the transient response of a system. But for this case, we're only concerned with those that are the time constant influences. So here's the raw data. We stuck the thermocouple into the boiling water, and we found that the final temperature we got to was about 92 degrees Celsius, which is a little lower than we expected. We started from an ambient temperature of about 25 degrees C, which is typical. So when we removed the thermocouple from the boiling water at 92 degrees C, it took about 375 seconds for it to reach a steady state value of 25 degrees C, which is considered ambient. What I did now is I normalized both temperatures by taking the measured temperature minus the initial temperature divided by the initial temperature minus the steady state temperature. And shown on the screen is an exponential decay graph of how that temperature decreased with respect to time. So you can see that the temperature suddenly drops as you insert or remove. It is a little quicker when you do insert the thermocouple into the water, due to the heat transfer, the heat of convection coefficient, and our heat equations. So if we take the log plot of this normalized graph, we get that we can make a linear approximation. And shown on the screen is the natural log of the normalized insertion and removal temperatures for a hot bath. I've shown that the equation for the trend line are shown on each graph, and in front of the variable x, which represents time, we get some slope. If we take the inverse of that slope, we should get our time constant for the thermocouple upon insertion and removal. The insertion time constant is 1.97, whereas the removal time constant is 78.13, which is something that we should expect. Our R-squared values for insertion are 0.97, and upon removal is 0.96, which means that we have our linear trend line does characterize the measured values well. So now I'm going to compare the raw data for the cold water bath, and upon doing that, we see that the behavior of the thermocouple upon insertion and removal does follow the same trend as shown in the hot water bath. Again, I normalized it and then took the logarithmic log of the normalized temperature and graphed it and got the time constant of 6.47 and 128, which is what was expected. My conclusion is that the time constant depends on if the couple is heated or cooled based off of the heat transfer coefficient H. The time constant when removing the thermocouple is much larger than when submerging the thermocouple. If we didn't know what bath we were putting it in, we were looking for an arbitrary time constant for our sensor. We have a mean removal time constant of 103, and we have a mean insertion time constant of 4.2. Our assumption is that the lump capacitance model doesn't take into account spatial gradients, and that we have a perfectly isolated system.